0 bias, forward bias, right? And reverse bias. If we have a P-N junction, something like that's P and that is N, and that's plus, and that is that is the depletion region, right? So we say at 0 bias, the electron energy will be higher than on this side. And that is the Fermi level. Goes like this. That is the conduction band, and that is the valence band. That is the Fermi level. Right? Now, when we forward bias, right, then this potential barrier decreases. Potential barrier decreases. So, and the Fermi level on this side is higher than the Fermi level on this side. Becomes higher. So could be like something like that is the Fermi level. And that is the Fermi level here. So the Fermi level on this side is higher than the Fermi level on the right side. Conduction imbalance. Potential barrier decreases when we apply forward bias. Right? And the electrons can move from this side to this side. In reverse biasing, this barrier increases, this higher. Right? So could be like if that is Fermi level F, then the Fermi level is great. That is the P side, and that is the N side. That is 0. Right? We apply equal to
0. Yes, sir.
We apply if we say A is
Greater than
0 positive, right? Or we can say we apply it,
negative.
yeah, we may call it negative. That's reverse bias. Reverse bias. So this is kind of a qualitative description of the, and here it's reverse bias, right? So we can say that this position from here to here, right? That is like E VBI plus V A, we can say. I would say V plus VR, we call it plus VR. But here we will have to add it with this. So I don't know what should we do if we call this as negative or positive. Right? Here it will be like this is the barrier now. And that will be E VBI minus VA.
Yes.
Say that one?
Yes.
So we can say that this is the basic equation. If VA is negative, then this becomes plus. Current, voltage, characteristics. Of a PN junction. So we have some assumptions for a PN junction, right? We said abrupt depletion rate. Abrupt depletion rate. Right? Also we said the doping level is low or low level injection. And the temperature is kind of high, and that is why the Boltzmann approximation is valid. You know, when the temperature is high, then we can replace the Fermi-Dirac statistics with the Maxwell-Boltzmann statistics, because that one does not matter.
Yes.
Boltzmann distribution, right? Approximate distribution is valid. Right? And the current is constant throughout the junction. The current is uniform to now, let us find before going to calculate the current voltage characteristic, we want to see what is happening at the boundary of the PN junction.
Yes.
Right? So the boundary conditions. Right? We know that from the previous knowledge that the built-in potential VBI is equal to kT by E to log of NA and D divided by NI squared. this was the built-in potential in terms of the concentration of dopants. Right?
Yes, sir.
Now, let us take, we want to bring, find like the Ni, the free electrons. So let us write it like this, and we log of N by Ni square, that is equal to VBI and E, right? E and to EVBI divided by KT. And if I take anti-log, right, then NA ND by Ni squared, that is equal to, right, e to the power EVBI by KT. Or if I am interested in finding Ni, then okay, so if we are interested in finding the concentration of electrons, so Ni square will be equal to our Ni square divided by Na, and D will be equal to e to the power minus E VBI divided by KT. Now we can find Na and D in terms of what is happening to the, the current on the P side will be controlled by the minority carrier electrons.
Yes, sir.
Because holes are much, it depends upon the number of the minority carriers to recombine with the majority carriers.
Yes.
So the current will be controlled by the minority carriers. Because majority carriers are very large number. So the more the minority carriers are available, the more there will be kind of a recombination.
Yes.
And the charge will disappear, and that will produce a current. Right? So we we consider here complete ionization too. Like complete ionization. Like at such a temperature is such that all the dopants are ionized. And the electrons are, for example, if it is on the N side, all the electrons are free.
Yes.
Because these dopants are ionized. So the number of free electrons will be equal to the number of dopants.
Yes.
Right?
Yes.
So the number of electrons on the N side in equilibrium. Here, N no means the number of electrons on the N side is equilibrium. Zero means equilibrium.
Yes.
Right? That will be equal to ND. All the on the N side, you will see on this side the doping is ND. On this side, the doping is
Yes, sir.
Na, the concentration. The atoms, the concentration of atoms.
Yes.
So the temperature is enough, large enough, that all the dopants are ionized.
Yes.
Because here we say that is the conduction band, and that is the valence band, then the energy levels of the dopants here is here, and there is a very small energy required for the electrons to come
To the
Here.
conduction, yes.
to go to the conduction band. Therefore, all the electrons at room temperature are supposed to be free, and that will be equivalent to the number of dopants,
Yes, sir.
right?
Yes, sir.
Okay, so also we say n I squared is equal to n naught and P naught, so, right? So we can write n at the P side is that is equal to n I squared divided by n a. Right? P on the, no, this is the number of electrons, that's the number of electrons. Here they are majority carriers. And the dopants here on the n side, they are majority carriers. What are the number of minority carrier on the p side? Electrons on the p side.
P side.
Here they are minority carriers. So that would be equal to Ni squared divided by P naught. Ni squared divided by P naught. But P naught is equal to Na, right? P naught is equal to Na because we say all the holes will be ionized. Right?
Yes, sir.
So now putting these facts here in equation 2. Putting these facts in equation 2, so Ni squared, right, over n on the n side, right, for Nd. Electrons on the n side, and for Na, we write this thing, Ni squared divided by electrons on the p side.
Yes, sir.
Right? So that is equal to e to the power minus e VBI divided by e power k. Right?
Yes, sir.
Now, this will cancel and P naught will go up. So n P naught is equal to n on the n side equilibrium and e to the power minus e will be bi over kt. That is the situation in equilibrium. The minority carriers in terms of the majority carriers. These are majority carriers.
Yes.
Electrons are majority carrier on the n side, but electrons are minority carriers on the p side. So look, the minority carrier is less than the majority carrier because this is less than 1.
Yes.
So the minority carrier are less than the majority carrier, and they can be described in terms of this equation.
Yes, sir.
Okay, so if we apply what? If we apply a biasing, forward biasing, right?
Yes.
If we apply a forward biasing, like this is changed to VB minus VA. We apply forward biasing. Then n at the P side, equation C will imply that N on the P side, but we do not write 0 now because it's not equilibrium. We have applied a field, external field.
Yes, sir.
Yes, sir. So it is not in equilibrium, right?
Yes.
So N and 0, we can still write it N and 0 because the majority carriers, they are so much on the N side, they have nothing to do with the field or whatever. They do not usually, they will not depend upon the electric field, right?
Yes, sir.
So here E and 2 minus E and VBI minus VA divided by KT. Or we can write this is N and 0 on the N side, majority carriers, and E, right, minus VBI divided by KT dot e to the power V A E, right, towards KT, right? R. This is equal to NP naught, right? So e to the power EB over KT. The electrons under applied field, at some applied field, is equal to the electrons, the minority carriers. The minority carriers at equilibrium on the P side, on the same side. Minority carrier in terms of when we apply some field, that is equal to the minority carrier when there was no field multiplied by this factor, which is greater than 1.
Yes.
Because it is EVA by KT. The VA is greater than KT.
Yes.
We replace VBI, right?
Yes, sir.
So that is equation number 4. Right. So when the electrons are injected into because of the applied electric field, right? It will be something like this. That is N, and that will be holes, right? Here I would say the electrons would have jumped here, and there will be holes available. Holes available this, here. So the electrons can at the junction, when you push electron from here, that is the EF. No, this is not. Yeah, this is the EF. But the EF is now higher on this side than this side, right? So when electrons are injected from the P side into the N side, right, they can combine here at the space charge region, right, with the holes that are available, so they will recombine. So they can recombine, and at the same time, when they reach here, there will be the concentration of electrons will be higher here as compared with this. So there will be a diffusion as well.
Yes.
Higher. Yeah.
Yes.
There will be a diffusion
Yes.
as well as a recombination. The current will be produced by two parts, a recombination or a diffusion, right?
Yes.
So here we will say in this situation NP will be greater than NP naught, right? Similarly, the question can be written, for the N side for holes. Pn is equal to P and 0 e to the power EVA1 kt. That will be for holes. The ideal P and junction current the ideal
P and junction.
P and junction current. So we said that if J is the current density, we said that electrons moving in one direction is equivalent to holes moving
And the other.
in the other direction. And if there are both holes moving as well as electrons moving, then the current will be added together.
Yes.
Because they are not moving like the same charge particle in the opposite direction. They are like the same charge moving in the same direction. Look, electrons are moving in this direction. They will be giving rise to, for example, electrons current in this direction. Holes moving in this direction, that effect is equivalent to electron moving in the opposite direction.
Yes.
So it means like the same kind of charges are moving in the same direction. Therefore, their current should be added together, right? So the total current density that should be equal to J P of x if it's a function of x, right? And J that is H xn, plus Jn minus xp. I have written as equation A in my notes. So the electron, the total current at the through the space charge region, that will be equal to the current at the edge of the n side, giving whole current, and the current density because of electrons here, this was minus x p and that was xn. So electrons, moving from here, if they inject from here, the electron concentration will increase as compared with the rest of this. So they will recombine here at the junction. So they will give rise current here. Similarly, hole on the other side, they will produce a current over here. right? So at the edge, E equal to, yes sir, 0.
Yes.
And we also said that it is a steady state if there are some excess electrons delta and their derivative with respect to time should be equal to 0.
Yes.
They should not, suppose they are not changing with
Time.
time.
Yes.
They might change with like distance, right? Here the concentration of electrons is higher as compared with the concentration of minority electrons on the other side. But with time they are not changing, so they are not a function of time.
Yes.
We suppose that, right? So if that is the situation and there is no electric field at the junction
Yes.
edge,
Yes.
then we say there will be no drift current.
Yes.
Because the electric field is, there is no electric field here.
Yes.
So at the edge,
Yes.
right? No drift current. Drift current is caused by the electric field. So it will be diffusion current. Drift current is caused by the electric field. And at the junction, we said that there is no electric field. We know that, if you remember, at the junction there was no electric field, just thus enough. The graph was like this,
Yes.
and these were the junction.
Yes.
You remember that?
Yes, sir.
So, the only current will be because of the recombination and because of diffusion.
Yes.
So, we know the current density equation from the diffusion, right?
Yes.
Like for holes at xn, that will be equal to minus E, and that was the diffusion coefficient for holes, and dp n on the n side, right? Holes on the n side by dx, and 8x is equal to xn. We are talking about the junction. Right?
Yes.
Now, for uniformly doped material, we can say that P and X, the holes on the n side, n side, that is equal to P and 0 plus P that was at the junction plus delta P, the axis holes on the n side at some position x. Some axis holes
Yes.
and some holes produced under equilibrium.
Yes.
Now, if we put this in equation 1, right? Equation 1 becomes, you notice this is a differentiation with respect to x. This is not a function of x.
Yes.
So the derivative will result in 0.
Yes.
Right? So J P the current density at the x side, right? That is equal to minus E dp and d by dx and p and 0 plus delta p n at some x, and that is equal to minus E dp d by dx of delta, right? P, what's the P was this one? P and x at x is equal to xn. Now delta for under these conditions with no electric field and steady state, there is an equation which gives you the transport of charge carriers. That is in the third and fourth edition. That is in chapter number 6. Right. Let's start with M bipolar. Transport. M bipolar means both type of carriers, charge carriers are there.
Yes.
So there is steady state, under steady state, and plus E equal to 0. That M bipolar transport equation gives us delta P and X is equal to P and naught and e to the power e to the power VA by KT minus 1 e to the power xn minus x divided by dp, the diffusion coefficient of holes, and P naught is the lifetime of holes. If we put this equation here, if that is 3, then 3 and 2 gives us what? J, right? T and xn. You know, for x is equal to xn. For x is equal to xn. So when x is equal to xn, that will be equal to 1. Right? So this will be equal to minus this is like we put here. There is a minus sign will be gone, and what we will get E G of P and 0 by D of P and G of P at 0 e to the power EVA over KT minus 1. That is question number 4. Similarly, this was the whole current, the electron current, right? The electron current. J N H minus HP, right? That is equal to E, and it was D N dy dx delta of N P at x, and at x is equal to minus xp. That is suppose equation number 5. Again from the M bipolar transport equation. From the M bipolar transport equation. Delta of N for electrons, right, at x, that is equal to NPO and e to the power xp plus x over kg and e to the power EVA over kg minus 1. So the current density, right, we put this here. And x is equal to minus xp. That is 5 U's. 5 U's of what? Jn at minus xp, the electron current density, that is equal to E dn and P naught. The electrons on the p side under equilibrium, divided by the same thing, dp and t here, n of 0 and dn, and like that E V is equal kT minus 1, the same thing here. So this is at the N side, at the junction, the current is controlled by hose.
Yes.
At the P side, the current is controlled by electrons. At the junction, at the edge of the junction.
Yes.
So the total current will be this plus
This. Yes.
this, right? So we can say that putting 7 and 4 in A, right?
Yes.
4 and 7
P. A.
A. Right? So we get what? J is equal to E d P P and 0 and by dP and P naught plus E d N and P0 by dN Tn0 comma and e to the power EV over KT minus 1. Right? Look, what is this? This is a number.
Yes.
This is a number. It has no dimensions.
Yes.
Here is current density. So this must be a current density too.
Yes.
So we call this a constant because this is all, these are all constants and they do not depend on the distance or whatever.
Yes.
Right? If we call this as saturation current and represent it by some symbol like JS. Right? The question, if JS is equal to E dP and P and O, right, divided by dP and tau up P0 and plus E dN and P0 and divided by dN and N0, then I can write J is equal to JS, right? And e to the power EVA by KT minus 1. We have considered this as a forward bias if you look at this, because we applied VA.
Yes, sir.
It's not VR.
Yes, yes.
So this is a forward bias.
Yes.
Forward bias. So look, if VA equal to 0, there will be no current, because 1 minus 1 will be equal to 0.
0.
But as we increase, right, the current, the voltage, right, the current density is kind of exponentially proportional to that.
Yes.
Right? It's like something like this. If that is
VA.
yeah, VA. Razan. Aha, seni. Любително. Razan kafe çağırıyor. Yüksel. Tam zaman da Rani de.
Last one.
So, if that is the voltage, applied voltage, so it will increase exponentially with the voltage. Right? Okay. This equation is like the ideal p-n junction current equation.
Yes, sir.
This we derive this for forward bias, but this is seems to be equally valid in the reverse bias. So you know, for example, the reverse bias is like a few times of the normal thermal potential, right? For example, VR is equal to minus 7 kT by E. That was the thermal potential, if you remember. So if we apply reverse bias of this value, right, then replace equation H, replace VA by VR. So J would be equal to J S and e to the power minus 7, I would say, kt by E, right? Minus 1. Oh, okay. Look, and for this, but there is like again E over kt. Okay, that on there. I replaced that VR with this, so there is an E by kt also, right? So that would be like e to the power minus 7, which is very smaller than 1, very, very small than 1. So that will be nearly equal to, right, minus Js current, which is a very small current. The saturation current is a very small current. So it will be in a reverse direction, right? Kind of like that, because it's not exponential until the breakdown.
Yes.
Say again? Huh? Yes, sir. And if we approximate this, right, for the forward bias, why first EVA by KT is very greater than 1. Right? If you say EV by EVA by KT is very greater than
1.
right? Then J will be equal to JS e to the power E V equal
KT.
KT. Right?
Yes, sir.
So log of J will be equal to log of JS plus right EVA
Yes, sir.
by
KT.
H. So at applied 0 could be like this. So it's kind of a linear relationship for log.
Yes.
The log of J is
Linear.
linear. And this will be like JS. Must be the one. Example is example by example that's okay.
Sir, mark.
Huh?
Very good. Sir, सिर्फ खाली एग्जांपल नाम हो रहा है.
Huh?
एग्जांपल नाम.
Huh. That will give you an approximation, an estimation of what is the saturation current. How much is the saturation current and other parameters that are there in used in PN junction current.